All right, one sec.
I have access now, thanks.
Oh my gosh.
I'm muted. I'm muted. Wow. That's amazing. Can you tell that
Alright,
it's been a while
one
since
sec.
I've been on? I have access now, thanks. Oh my god. Welcome to AoT BCS number 36. I am the Cosmic Kid.
And I am MC M33.
How's it going, everybody? MCM33, what are you drinking tonight?
I am drinking this IPA called Elysian Space Dust. There is a very happy hop on
Oh,
the label.
I am jealous. I am enjoying a nice Shiner Ruby Redbird.
Hey, Texas.
Classic Texas beer. But yeah, it's been great. I've been away teaching for the past several months, so I haven't been able to be on. So clearly, I got some rust I need to shake off. But I'm happy to be back with my best buddy MCM33. Shall we get started with the announcements then?
Yes, please.
All right. So welcome to Astronomy Second number 36. If you want to participate in trivia, you can head on to tx.act/AOT trivia. The link is also going to be in the YouTube description. The theme this week this month is astronomy themed food and drinks. And so if you win, we'll send you an email and get you some cool swag.
Like and subscribe on YouTube, and you can hit the bell button for notifications as to when we have new streams scheduled. And I think when we're going live, I'm not entirely sure. I personally don't use the bell button. I don't
But
know
it
about you.
helps with the algorithm, the whatever, however that works. It helps somehow. Puts us over the other astronomy taps.
The god of YouTube.
Hmm.
Your offerings.
Follow us on social media at AOT_BCS on Twitter and Instagram, and at AOT BCS on Facebook. You can head on over to astronomyontap.org/events to see all the Astronomy Tap events that are available.
Yeah, please, please, please support what would have been our normal venue, the Grand Stafford Theater in Bryan, Texas. To do so, you can Venmo at Jose-Quintana-20, and you can put Stafford Tip in the description so he knows what it's for. Again, please, I miss the Grand Stafford personally. I cannot wait to go back.
It's a great place. If you want to help support us, you can send us some money on Venmo or Cash App at AOT BCS. If you send us $15, we'll ship you an AOT t-shirt, which has this lovely logo on here that one of our grad students designed.
Right. Our next Astronomy on Tap is the third Wednesday, June 23rd, 2021, and we hope to see you there. I'm honestly, Cosmic Kid, why is there a Pikachu face there?
I don't know.
Okay.
Who knows?
I thought I'd ask.
Well, I guess the whole thing is you're shocked that's on the third Wednesday, but of course it's on the third Wednesday. That's the whole meme, right?
Oh, this is true.
Here I am meme-splaining at you. Don't forget to put your questions in the live chat. Don't wait and forget. Go ahead and put them down, and we'll get to them the second we get. And if we aren't able to answer your questions now, we'll save them for a burning questions segment in a couple of months. And that is it for the announcements. So I guess we can go ahead and welcome in our first speaker.
Yeah.
Our first speaker is Felix Martinez. Felix is I guess you're in that weird in-between phase of being a junior and a senior, so I'm not sure what to call you.
Yes.
But you are about to enter your senior year at Texas A&M, and some fun facts about Felix. He is the foremost expert in the physics department on 3D printing.
Thank you very much, Cosmic Kid.
Yeah, so Felix, take it away with your sure to be pretty awesome talk.
All right, so my talk is over black holes and falling through them. Now, I thought it best to start with a trivia question. So I wanted to ask, you can feel free to type this into the live chat or just think about it. But I want to start off with what will happen to Earth's orbit if the sun was replaced with a black hole of the same mass? So I'll give you a few seconds to think about it. Well, the answer, nothing. That's because gravity is actually dependent on mass and not the matter that makes up the mass. So since the sun is going to be replaced with a black hole that has the same mass, nothing will change with the Earth's orbit, nor will it change with any of the other planets or asteroids within our solar system. So I thought it also best to continue on to go over a brief description over how black holes are made. Now, for the entire life cycle of a star, there is a constant battle between two forms of force: an inward force, which is gravity, always pushing the particles closer and closer towards the center of mass, and an outward pushing force, which is more so a heat or pressure force. This heat or pressure force is being caused from particles being condensed so tightly from the gravity that they form a new particle. So for example, if you condense two hydrogen atoms together, they form a helium atom. And this continues on for hydrogen to helium, helium to carbon, carbon to oxygen, neon, magnesium, silicon, and finally iron. Whenever the star gets to the iron phase of its life cycle, it can no longer condense further down into a denser element. So the energy source, the source that is pushing against that of gravity, stops, causing gravity to win in a sense. This initial stop results in the inner core of the star imploding upon itself at roughly 1/4 times the speed of light. This results in a shock wave that is so strong that the outer layers of the star get shed, and this is called a supernova. I will also say that for our sun falls into this massive category where it will stop at roughly at around carbon, the helium to carbon stage. Our sun does not have as much mass as required for this pressure to continue pushing into the star to get to the iron stage. Our sun will not explode, so you don't need to worry about that. An example of a supernova is the Crab Nebula, or Messier object number 1, for those of you who are interested into looking into the Messier objects. This cloud of interstellar matter is the outer layers of the star that were shed in the violent implosion of the core. A star is turned into a black hole, and whenever the collapsed core is roughly that between 1.5 to about 3 solar masses, anywhere within that range. After that, gravity pushes all of the matter so densely together that it implodes into a black hole. So now that we know where black holes come from, I thought it best that we were to visit the black hole that replaced our sun. So we sent a crew of brave astronauts towards the center of our solar system to visit the black hole. And once they arrive, they notice that they cannot actually see the black hole. Instead, the black hole is not there. It's black. They can't see anything through it at all. Instead, what they see is an accretion disk. This accretion disk is made out of dust and gas, which is left over from the initial explosion from the core collapsing upon itself. The remaining dust and gas that was left gravitationally bound into the system was stuck within this orbit and forms this accretion disk. Now, our astronauts were able to notice that the event horizon of our black hole is roughly that of about 10 miles. This is because this is the black hole. This black hole has the mass of about 1 sun. It's formed so small that an object the mass of our sun is compressed. If an object the mass of our sun is compressed down so tightly to that of about 10 miles, it will form a black hole this size. Now, once one of our astronauts decide that they want to go venture into the black hole, trying to take data and understand what sorts of physics they will encounter within the event horizon and try and discover new types of matter there. Now, for our astronauts on the space shuttle, they noticed that whenever our astronaut, our brave adventurer, approaches the black hole, they will begin to slow down the closer and closer they get. Eventually, they'll notice that the astronaut will stop right above the black hole. And instead of seeing them go through the black hole, they will see the astronaut eventually disappear. They will never see the astronaut venture into the event horizon. This is because time is run differently relative to the space shuttle versus the astronaut that falls into the black hole. Since the black hole is so massive, time runs a lot faster the closer you get towards the black hole. Kind of like the movie Interstellar, if you're familiar with that. Whenever the crew approaches the planet with the giant tidal waves and they leave the planet, they notice that the time that it took for them to take that trip was much drastic than the time on the spaceship that was just off the planet. A similar thing would happen when going towards the black hole, just much, much more drastic. Now, for our brave adventurer who falls into the black hole, time running for them will feel normal. Actually, when they get there, the first thing they'll notice is some very strange light distortions. This is mainly seen through the accretion disk. Now, the accretion disk is the perpendicular form of matter or of dust and gas. And what we see here is a halo. This halo is not physically there. It's bent around the mass of a black hole to where it appears that it lies on top and below the black hole. This is due to the mass of the black hole. It's so massive that light itself is being bent around it to fall onto the observer's eye. That's not only the light distortion that they'll see, they'll actually see a replication of themselves throughout the black hole. So since the light is being bent so drastically the closer you approach the black hole, in front of you, if you look into the black hole, you'll see the back of your head. That's because the back of your head, the light from it is being emitted and being pulled into the black hole so strong that it will wrap around and fall onto the observer's eye. It's seen more drastically when looking right or left, kind of like when you hold two mirrors parallel to each other. If you look through it, you will see an infinite number of yourselves until you slowly disappear off. A similar distortion will occur whenever you look near or around the black hole, the closer you approach it. The only difference is it'll bend around from the gravity of the black hole. It won't just be flat and straight. So not only will light distort, but also, like we mentioned before, time is going to be very drastic here. It'll be much, much different here than outside of the black hole. If our astronaut turns around before they enter the black hole, they will see streaks of light crossing the entire universe, everything they can see. Now, these streaks of light are actually not asteroids or comets running through our solar system or our galaxy. No, they're actually stars in our galaxy that are running through the orbit of the Milky Way. This is because light is passing so slowly here that outside, relative to the astronaut, it's running so fast that they just see beams of light of these stars. They will see stars born and die while going through this. And they will see collisions of galaxies, of Andromeda to the Milky Way, all in this one moment. Now, when our astronaut goes through the event horizon of the black hole, they will encounter this strange process of spaghettification. This is what happens whenever gravity is much more active, is much more stronger, the closer you are to a black hole, the closer the object is to a black hole relative to an object further away. So since this astronaut has a height to them, their feet are much closer to the black hole than their head. Even though it's a small amount, it's still closer. And since they are so close to the black hole, their feet begin to get pulled down through the event horizon while their head falls down at a slower rate. this causes a sort of funnel of matter as you get compressed down into some sort of like spaghetti shape. It's not a pleasant experience. And this is only caused from our astronaut venturing through a small radius black hole. Now, the difference between a small radius versus a large radius black hole is we have a side-by-side scenario right here. Now, what we have on the left are white dwarfs. These are the remains of less massive stars like our sun. Whenever our sun will eventually run out of fuel, they will not create a black hole. Instead, they will create a white dwarf, which is mainly just the carbon left over from it. If we have this white dwarf approach a small radius black hole, it will have to go through the spaghettification process to fit. The black hole is not going to have them stuck right above the process. No, it will pull all the matter into a size that will fit the radius of the black hole. However, if this if the same white dwarf enters a black hole that has a much, much larger radius than that of the white dwarf itself, it'll be able to fall through and not experience the spaghettification process through crossing the event horizon. Now, I hear you say, does such a black hole exist? Do black holes even get to a size where they can swallow entire stars? Well, the answer is yes. Here is a very famous image that I'm sure everyone has seen at some point. This is the first image taken of a black hole. This is the supermassive black hole found in the center of the galaxy M87. This black hole is so massive, it has the mass equivalent to about 6.5 billion times the mass of our star, of our sun. Now, this black hole, since it was able to fit that much mass inside of it, it was able to have an event horizon that could swallow in a majority of our solar system. So if we were able to venture through a supermassive black hole, such as this black hole, M87's central black hole, or even our own Milky Way's central black hole, because every galaxy has a large supermassive black hole within it. If we were able to venture to that, then we will be able to kind of ignore this spaghettification process. We wouldn't have to worry about being stretched thin. Now, these black holes are actually not believed to just be caused by the death of a star. There is no star that is so massive that it could create just this black hole, a black hole this size by itself. We believe these black holes are caused from, of course, it begins with the death of a very massive star, and then you are left over with a black hole of a large mass. This black hole would then, or could then, come into contact with another massive black hole, and it would increase its mass. We've encountered this, and we've seen this process go on, and we believe that the supermassive black holes found at the center of these galaxies are as a result of these large black holes coming into contact of each other, colliding to form a larger black hole with a larger effective radius, something that we could venture through and without having the pulling process. That concludes my talk. Thank you very much for listening. Now, if you have any more questions, feel free to ask in the chat. I'll be here to answer anything you have.
Thank you so much, Felix. That was a great talk.
Thank you.
Learned a lot. So we do have a couple of questions in the chat. We have a question from Jessica. How does time go faster close to the black hole? I think she meant slower close to the black hole.
Yes. Since you are approaching the black hole, gravity is behaving, or time behaves in a weird way around such a massive object. For relativity, if you are outside of the sphere of influence for the black hole, you will notice that the person inside of the black hole will run, or closer towards the black hole, will kind of slow down. They will move a lot slower due to this change of gravity, this gravity that just interacts with the time that the other person who is in the black hole experiences. Time running relative to them is a lot slower than the time outside of the sphere of influence for the black hole. It's due to the mass of the black hole and the gravity caused from it.
Awesome, thank you.
All right.
Yeah, this next question is also from Jessica. If we
Okay.
can't see something disappear into a black hole, how do we know that this is what would happen?
Okay, we know that spaghettification does in fact happen from actual observations of stars interacting with black holes. Now, this entire talk was over theoretical black holes that don't actually have a spin to them. Just the math is a lot easier to work out. When we actually observe black holes in our universe, in our galaxy, every black hole has a spin to them because every star has a rotation, a spin to them. And because of this rotation and this spin, due to the law of angular momentum, it continues even after the star explodes and forms the black hole. And if we have a binary system of a black hole and another star, if they fall close together, we will see the spaghettification process of the star kind of tail off and orbit that of the black hole from the mass and the hydrogen and the outer shell of the star get pulled into the black hole. That is an example of a massive object trying to enter a black hole that is of a small radius.
Awesome. We have a question from Maddie. How long would it take for a person to get spaghettified? Would it be an instant process or would it take a while?
Okay, well, when talking about black holes, you have to think of time relative. So for the observer outside of the black hole, so for our space shuttle, they will see that it will take so long that they wouldn't even be able to see it happen. They wouldn't be able to process it. It will go on for many, many human lives that they wouldn't even see you enter it. Your light will be redshifted to where you'll be invisible. However, for the actual astronaut going through this black hole, such as the example that I showed, it will be a few seconds, and it's kind of the same way as if you land a rocket on our atmosphere, or a crash an asteroid would be a better example. Crash something into the Earth, the gravity will pull the object closer towards you if you are in an unstable orbit, and it'll just take about a few seconds for this interaction to occur for the actual astronaut experience it.
All right. We've got one more question. This one comes
Okay.
from Joshua. Why would the astronaut in your example go through spaghettification despite having such a low mass?
So it was an example that I kind of thought of that would be fun to follow along. I actually am not quite sure if the mass of a normal human would be able to fit through a black hole of 10 miles long that will encounter this spaghettification process. I know for a fact that if we were to have a much massive object, such as a star, a moon, anything larger than 10 miles, it will fall through the spaghettification. I just wanted to kind of make a fun story as they were entering the black hole, kind of giving them a motive so you could hopefully get invested in this story.
Anthropomorphize the science.
Yes.
One final question for you, because we missed this at the intro. What are you drinking tonight?
Oh, I am having Angry Orchard apple cider. I'm having the green apple version. Very sweet. I like it.
That sounds delicious. All right. Thank you so much, Felix.
Thank you so much for having me.
All right, M33, what do we got next on the docket?
Well, there's this person I know who's going to be coming up next, and you also all know and love him, those of you watching. It's been a while, but he's back with What's Up. I give you the Cosmic Kid.
Hello, thank you for that. So this time I'm doing something a little bit different. Instead of slides, I'm going to show you a couple of cool other things. So what's up this month? We've got a total lunar eclipse coming up in a couple of days, actually, May 26th. Now, Bryan College Station area is just on the edge of where you can see the totality of the eclipse. You can go to this website, timeanddate.com, if you live in non-BCS area to see what it would look like from where you live. But this is a good way to figure out when it'll be up and what it will look like where you are. So for us, the whole thing starts basically at around 4 a.m. in the morning. And it looks something like this. You'll have the penumbra of the edge of the Earth's shadow will initially cross the moon. Nobody will really notice anything. But the umbra, which is the central part of Earth's shadow, crosses the moon, and then you get the partial eclipse. And time keeps moving on. Now we're at about 5:30 in the morning. And then you hit about 6 a.m. in the morning, and you get the full eclipse. So this is going to be a total lunar eclipse. What will happen is the moon will look just like this. It'll look kind of reddish, and you'll have maximum eclipse for actually only about 10 minutes or so. And then the eclipse will be over, because that's basically right when the moon will set, because that's basically around sunrise as well. But yeah, if you're awake at around, let's see, what was it, 6 o'clock in the morning, you can go out, wake up early, make some coffee or whatever, check out the total lunar eclipse. It'll be pretty fun. The other thing I wanted to show y'all is this website called Spot the Space Station by NASA, which tells you, based on where you are, when the ISS will be visible. The ISS is actually super, super bright, and you can really easily see it, even in the middle of a bright city, without any binoculars, telescopes, or anything, just with your naked eye. So you can search your town or city, or you can just scroll in and scroll out as you will. And then when you click to see sighting opportunities, it'll show you when the ISS will be passing over for the next week. So the best chance for us in College Station to see it was actually last Monday, when it was visible for a full 5 minutes and it was really nice and bright. But over the next couple of days, there's going to be plenty of sighting opportunities. It's only going to be visible for about a minute each time. But if you keep looking at this website, you might find yourself with a better chance. And this is pretty accurate. For if it says the ISS can be visible at 11:07 p.m. for 1 minute, it's going to be visible at 11:07 p.m. for 1 minute. The NASA people, as it turns out, know their stuff. So as long as you're someone who can make it to things on time, you should be able to spot the ISS. And keep an eye out for when it's visible for much longer. And that'll be a great opportunity, especially if you want to take photos. You might be able to do that when it's visible for a much, much longer time. And that, my friends, is what's up this month.
Thank you, Cosmic Kid. I have memories of going up to watch the ISS with my family. They are really good. It's like they say 5 minutes. It's visible for 5 minutes. It's amazing.
Absolutely, yeah. And if you have binoculars, a telescope will probably be too difficult to point quickly, but binoculars, you can actually make out a lot of details on the ISS. It's really quite amazing.
Yeah.
Anyways, I don't think we have any questions. We have somebody in the chat saying there are good apps for spotting the ISS, including ISS Detector. So there's a lot of things like that. So yeah, there's a lot of fun things to look for ISS or other satellites as well if you're a satellite hunter. But I think next up we've got In the News with Dark Matter Dude. Dark Matter Dude. Hello.
Hello.
What are you drinking, Dark Matter Dude?
I think I'm just drinking a normal Moscow Mule. I think.
Those are tasty.
Yep.
Yeah, and you've got the copper mugs and everything.
We do. Yeah. Yeah. We're all serious business here at Astronomy on Tap.
Of course. So, Dark Matter Dude, tell me, what's in the news?
Yeah. Well, I'm gonna share that with you. So let me just share my screen. And we should be good now. Okay, so hi, my name is Alex Riley, aka Dark Matter Dude, and we are going to talk about some of the headlines that you may have seen in the news and describe all the kind of science and background that you might miss. My mouse isn't working. Okay, cool. Wait, did it skip? Oh boy, there we go. Okay. Right. Okay, so this is a story that we talked about right around a year ago, I think. You may have seen a little bit of chatter about the Defense Department releasing a whole bunch of information about UFOs and all of this stuff. This isn't new if you've been following us for the past year or so. I'm not going to go into very long explanation about this. It's not aliens. It's just not. And I actually made a hot link to take you to where I talked about this story a while ago. So you can go to tx.ag/not aliens, and it'll bring you to, I think it was AoT BCS number 24 or something like that, and it'll take you like right towards the middle where I was talking about this story a year ago. It's not aliens. I'm just going to preface it with that. So moving on. Yeah, so detecting dark matter with planets. I love this story because exoplanets are kind of just this kind of cool thing that everybody loves, and dark matter is what I actually study. And so merging the two is really awesome. Right, so one of the theories about what dark matter is, so dark matter is kind of this sort of invisible matter that we think governs how galaxies form and evolve over time, what makes them clump together and form. One of the ideas for what the nature of dark matter, the particle nature of dark matter, is a so-called WIMP, a weakly interacting massive particle. And the whole idea here is that it's a particle that interacts very rarely with like normal standard model stuff like protons and electrons, the stuff you and I are made of. But it does sometimes. And when it does, dark matter particle will come in, scatter off of a proton, and it'll generate energy, maybe gamma rays, maybe something else, but it'll generate energy. And that energy can sometimes generate heat. So the idea here is planets are, always traveling through dark matter, and the idea is that all these interactions that the dark matter particles could be having with the standard model, like the protons and electrons in the planet, could actually, the energy that's given off could actually heat the planets and brown dwarfs, which are kind of like which is kind of an intermediate step between planet and star, big planets and small stars. So theoretically, this could, like, people have done these calculations. This effect could heat planets and brown dwarfs to about 1,000 degrees Celsius, which is actually way hotter than like planets normally get. So, like, for example, Jupiter is like minus 200 degrees Celsius, something like that. And so this would make the planets actually very, very hot. And so the idea is, okay, we have this model for how this interaction could work. So let's test it. If we look using current and near future infrared telescopes to look for the heat signatures of this warming up at a whole bunch of exoplanets that are nearby. So for close by things, you would want to look at like exojupiters, Jupiter mass planets around other stars. And then another really good test would be for looking at brown dwarfs, which are more massive, but further away from us towards the inner galaxy. And the reason you want to go towards the inner galaxy is because that's where all the dark matter is, right? The density of dark matter is much larger, closer in towards the center of the galaxy. So if you look, and if you find, basically the idea is, if WIMPs are the correct particle model for dark matter, you should have most of these brown dwarfs be way warmer than they should be. And if they're not, that puts pretty strong constraints on what the WIMP is allowed to be. So yeah, this is super cool. Next up, don't fall apart just because China's rocket did. So this kind of took the entire like space community by surprise. So around May 6th-ish, a whole bunch of satellite trackers, and later the Chinese government came out and said, hey, we put a rocket up, and it's gonna fall on Earth somewhere at some point soon. And everyone went like, what? But yeah, so the idea here, so this rocket was launched up to send a core module for the new Chinese space station that's being built. And the rocket fell off, kind of as planned. We think, maybe. There's a lot of details that we don't know about this. But we didn't know what the landing location was going to be. And the whole idea here is that because way up high where this interaction happened, there's very low air density. The rocket itself, observations that said that it was tumbling instead of just falling. And it was moving very fast. So all these things combined means that the very slight change in where it was or how fast it was moving or exactly what the airflow in that region looked like could change pretty drastically where the rocket would land. In the end, it actually turned out okay. So it probably was going to turn out okay anyways. Again, Earth is mostly water, and even the parts that are land, a lot of times no one lives there. There's a lot empty land. And so what ended up happening was the May 9th, time zones are weird. May 9th, like UTC. The rocket fell in the Indian Ocean, 50 kilometers from kind of west of Maldives. And so everything's fine. No one got hurt, which is really good. But it kind of illustrates this point that we humans, I don't mean to say this is like even this is a strictly Chinese government problem. Like, we humans are not very good about dealing with our space debris. And if we continue to be bad at it, it's going to bite us in the butt in the future. And this was one case where it really could have. An exoplanet where there shouldn't be one. This is fascinating. So in exoplanet studies, one way to kind of detect and confirm exoplanets is through what's called direct imaging. So this is when you actually take a picture of the star, put some kind of light blocker, or like you block out the light coming from the star itself so that you can see light from stuff that's immediately in the vicinity of the star. So direct imaging. People tend to do this using infrared. There's a couple different reasons, but one that's really useful is that this method is really good at detecting hot young planets. So in order to just detect those types of planets, you want to look in the infrared because if it's hot, it's generating infrared waves. In addition, the star is usually fainter in infrared than it is in visible. So there's less light coming from the star that you have to block off. So, oh boy, is it going to go? Yes, it is. Okay, good. Right. So this is about 5 to 8 Jupiter masses was the planet that they found. This you can see in the picture here. The star blocked is in the center, and then the patch of light labeled B, that's the planet. It's about 5 to 8 Jupiter masses, probably around 6. And what's interesting about it is that it's that massive and it's very far away from its star. It's about the distance from the sun to Earth. It's about 110 times that. So that's way past where like Pluto usually is. Like this thing's very far out. And it's kind of posing a question to like, how do you get a big planet that far out? So there's kind of 2 ways that you form planets. The first one is direct collapse. So the idea here is that you have a whole bunch of cold gas that just almost immediately collapses just under gravity. This is how stars form. This is how you can get binary stars to form. But the idea here is that it's actually too massive to form this way. The idea is that it's just kind of too far away. You can't really expect it to form that way. The other idea is core accretion. So the idea here is, if you have kind of like a debris disk, so kind of like the asteroid belt around our sun, and you have particles kind of colliding with each other. Eventually they clump up, form bigger and bigger clumps. Those clumps eventually get large enough to just gravitate a whole bunch of stuff towards it, and you can build up a planet that way. There's a couple problems with this one. The planet is too far away from the star for that to happen. Way this far out, the density of particles is just too small to have that process get going. And then the other part is that there's really no companion planet. So the other idea would be that maybe it formed closer in to the star and then got ejected out by some form of 3-body interaction with another planet that's right next to the star. But there's no other planet that these teams have found, and so there's nothing else that could make that 3-body interaction to eject this planet that far out. So yeah, this is a mystery. There's a massive exoplanet where there really shouldn't be one, and no one has a great idea of what made it that far out. Yeah, so then I like to end this with just a kind of fun imagery here. So last talk gave a great summary about black holes. So this is a fun imagery about binary black holes. So same idea. Setup here is that you have two black holes orbiting each other, and each one has an accretion disk around it. And if we rotate it so we were just looking at things like face on. If we look at things edge on, we get some really cool images here. So you see this kind of characteristic double loop thing going on. We saw that in the in Felix presentation, the first presentation. But then if you kind of have these two black holes go in front of each other, you get kind of knock-on secondary effects. And so like the blue one is about to get super distorted around this the black hole that's kind of towards the front. It's the same kind of like Einstein's theory of relativity, general relativity going on. But so that's the first thing. It was super cool. Secondly, very related, is that the actual first calculations that figured out this kind of characteristic two circle shape were actually done in 1978 by Jean-Pierre Luminet, who did, this is an image of his calculations on the right. So the same physics is going on, but those calculations used punch cards, which is like early programming days of computers using punch cards. And the visualization here, each of those dots is drawn by hand by the guy who did this. So I just found that fascinating that we went all the way from doing these calculations by punch cards and drawing out our images with little dots by hand to now we have these really sophisticated simulations that can do all this stuff going on. So yeah, that's what was in the news this month.
Awesome. Thank you so much, Dark Matter Dude.
That drawing was so cool.
Yeah. Done with punch cards, man. So I actually have a question for you. We made that leap in 1970, that's 50 years ago, from punch cards and drawing by hand to these powerful simulations. What do you think the next leap is going to be in astronomical simulations?
I mean, there's so much. So right. So in terms of like these black hole simulations, I know very little. About this. But I think still we want to get to the point where we can simulate kind of what's going on with more complex models. So we talked earlier about, we kind of think we understand what happens if the black hole's not spinning, but we think most black holes have some sort of intrinsic spin, and that changes everything about all of the general relativity going on. And so I think doing detailed simulations of that is what's there. But there's also like separate from the black hole stuff, there's galaxy formation simulations and all types of other things simulating different types of dark matter. So yeah, it's a good time if you like simulations. There's lots of stuff that you can do. That's
great. I don't think we have any other questions in the chat so far. So thank you so much, Dark Matter Dude.
All right.
Next, I'm 33.
Next up, we have Astroman, aka Justin Cole. There we go. So Justin is going into his second year in the astronomy graduate program at Texas A&M, and he's also one of the organizers for this very Astronomy on Tap. Some fun facts about Justin outside of research. He likes to play with his doggos, slay imaginary dragons, hang out with his plants, and chill with friends. Right, Astroman? Take it away.
Awesome. Okay, so today I wanted to talk about distances and measuring stuff, because astronomers, we always talk about like, oh, this thing, it's parsecs, or this, it's so many light years. And a lot of people don't really, like grasp how far that is. And so I thought it would be fun to just like, let's measure stuff in beer instead. And in order to do that, we have to make some simplifying assumptions. So a lot of these are going to be like safe assumptions. I could have made this way more drastic, but I was like, whatever. So we're gonna assume that one beer comes in like these weird foot tall cylindrical cans. And we're gonna assume that those cans, like, we can just attach them to each other because we're gonna be like stacking them up and measuring stuff. And then we're gonna assume that humans have that, there's these theoretical humans that have indestructible livers and they can drink 10 beers every day and live, to be 100 years old. And then we're also going to assume that all 7 billion humans are 21 years or older for very obvious reasons. And then I'm going to define, like I said, we measure stuff in parsecs and, light years and what's a megaparsec. So we're going to define a new unit of distance, and that's going to be the beer year. And basically that's how tall our stack of beer will get in 1 year if we just stack everyone's beers up kind of in a line. And that's going to be 7 billion humans times 10 beers every day times 365 days in a year. That's 26 trillion feet. So already it's, that's ridiculous. That's ridiculously far. But that's what we're going to use. And so, to put it in like kind of context, that's 5 billion miles. The human mind can't really imagine a billion. So like, we're already getting kind of crazy. And then just, as a disclaimer, you cannot safely drink 10 beers every day for 100 years. Like, you can't do that. Our hypothetical humans can. I would definitely not try. So we're going to start off with something that's pretty easy. We'll just measure a mile. This is, 5,280 feet. That's 5,280 beers kind of stacked on top of each other or, next to each other. So it's 528 people drinking in one day. Like, we can do that. We can do that pretty easily. And so here you can see I've drawn this short black line here. That's Texas A&M campus. That's about 2 miles across. And so, if 528 people can drink for one day and stack their beers into a mile, then, we can easily do this across the campus with, about 1,000 people in one day. We start to get a little pressed when we try to do Bryan College Station. That's about 15 miles, 80,000 beers. Take maybe all of the grad students in all the Texas A&M campuses could maybe do this in a couple of weeks. It would take some time for us to kind of stack all of these beers up together. And so we haven't even come close to like reaching a beer year yet. There's like thousands of people drinking for weeks at a time trying to accomplish this at this point. And so, if we measure Texas is almost 800 miles from the very, very west point to the very, very east point. And this is a little over 4 million beers. And so, we're getting a little closer. It's still less than 1% of a beer year, but now, we've been like lining all of these weird foot-long beer cans. We've been lining them up on the ground, but we want to measure stuff in space. So we're going to assume that it doesn't fall apart, and we're just going to like pick this stack of beers up and point it into the sky. But we have to be careful because we've already, like, our stack of beer has already passed the height of the International Space Station. It orbits Earth at about 254 miles. So as we're kind of like swinging this, 800 mile long stack of beer into the sky, we have to be really careful about when we do this and, where the ISS is and where all the other satellites are. And I'm sure we could ask Yaswant, and he'd be happy to help us with getting this thing kind of pointed in the right direction. And so we're gonna try, like, let's try to poke the moon with this stack of cans. This is it's a little over 1 billion beers. It's 250,000 miles. It's 1.26 billion beers. And actually, we're getting pretty close. Like, this would take about 90 days for us to do this. It's about 1/4 of a beer year. So we're getting close to, like, we've been at this for 90 days, and we finally kind of poked the moon with our giant stack of cans. And so now we want to try to poke the sun. Let's see if we can, make it all the way there. No chance. There's no way. This is 94 million miles. That's 500 billion beers, which is, 540 beer years. This would take, if we measure a generation as 100 years, this would take, 5.5 generations of humans to, like, achieve this. And they're drinking 10 beers a day, every single day, and everyone's, like, collecting their cans and stacking them into this thing. But we're going to assume that process is really efficient. There's no downtime when we're stacking. You drink the beer and it just goes in the stack. So, this is, like, we're kind of reached the limit of our generation of beer drinking, can stacking humans, but that's okay. The human civilization is going to continue living, so they can just keep stacking these beer cans until we kind of measure stuff in the universe. So moving to the next closest star, Proxima Centauri. It's this little, it's in this little dot here, diamond. That's 4.243 light years. It's the closest star to Earth that we've discovered yet. This is about, I'm not even going to say how many beers this is anymore, because, we're starting to get into huge numbers that, I don't think my brain can comprehend what a 1 with 17 zeros after it means. But we're just going to start measuring things in beer years. So it's about 51,000 beer years. This would take 51,000 years of everyone, drinking 10 beers a day and adding their cans to the stack. This is at least 51 generations of humans. At least, because, generations don't just, like, line up one after another. There's overlap. And so, this is really, we have to kind of, if we wanted to try this, and I suggest we don't, but if we did want to try this, we'd have to kind of stay within our solar system. I think the limit would probably be like Mars or Venus. Every human alive right now, we could probably achieve that if we had these indestructible, weird foot-long beer cans that we're pretending that beer comes in. And so let's just look at some pretty pictures of stuff that's in the Milky Way and see if we can, is it possible to measure those with our new way of measuring stuff. So Orion's Nebula, this is M42/43. You can find it kind of in Orion's sword, just below the belt. This is 24 light years across. So we know we couldn't measure the distance to Proxima Centauri, so we can't even measure the distance across Orion's Nebula. This would be a little under 30,000 beer years. This would be quite a feat. This would be a dedication. But if we had been drinking beer for the 200,000 years that humans have been around, maybe we could have achieved this. But the coordination, takes a bit. However, it's 1,344 light years away. This is 1.6 million beer years. There's no way we could possibly ever, accumulate enough, whatever our cans are made out of, to kind of stretch out and measure how far away Orion's Nebula is. And the same goes with the Pillars of Creation. They're a bit smaller, but they're still 5 light years tall. And so that's, 5 light years, that's only about 6,000 beer years. So if we wanted to try to measure kind of like how tall they are, we could try that. I think that wouldn't be like a terrible effort. But it's 65,000 light years away, and that's, almost 8 million beer years. There's no way we could possibly do this. It's just, there's no chance. And so the Crab Nebula, which if we measure from the longest, if we measure the longest diameter across the Crab Nebula, it's about twice as large as the Pillars of Creation or the Eagle Nebula. So like maybe 12,000 beer years, man, pushing it. Maybe we could do it, but again, it is also about 65,000 light years away. So that it's just impossible to try to like measure how far this thing would be with our long aluminum measuring stick that we're kind of like sticking out into space. So we've talked about like stuff that's in the Milky Way. We haven't even left the Milky Way yet. I guess I should say that. So let's talk about just the Milky Way itself. The sun is about 24,000 light years away from the center of the Milky Way galaxy. This is, almost 30 million beer years. We're kind of approaching the limit of, we're kind of approaching like the limit of our ability to like understand how many years it would take to like build this giant stack of beer cans. And so that realistically, that's only about a quarter of the diameter of the Milky Way. And so that would take 120 million, that's 120 million beer years. And that would take 120 million years for us to stack these cans, just so they would reach across, go from one end of the galaxy over to the other. And so, this is like ridiculously large. Even the stuff before, even the nebula and stuff that we were talking about before was ridiculously large, ridiculously far away. And we haven't even left the Milky Way yet. So let's do that. Let's talk about Andromeda, which for some of you may have noticed that that's my background image. Andromeda is actually about twice as large as the Milky Way. So that's, a stack of cans would take 240 million years for our, this line of cans to stretch across there. And that's not even the daunting part of this whole thing. The distance to Andromeda is 2.5 million light years. That's 3 billion beer years. That's like 25. It would take about a quarter of the age of the universe for humans to achieve this. Like we're approaching the age of the Earth, trying to kind of build this measuring stick to poke Andromeda. And if we move even further, and we try to measure out to the Virgo cluster, the Virgo cluster, actually Felix was talking about it, the center of the Virgo cluster is this galaxy here, and that's M87. And at the center of M87 is the wonderful picture of the black hole that Felix was showing us. And so if we try to measure this, that's 65 million light years away. The universe is not old enough for us to have tried to make these stacks of cans. That would take us 78 billion years of drinking 10 beers a day and trying really hard to stack up all of these cans. And it just, we wouldn't, 78 billion years, that's a very, very, very long time. There's just no way we could, measure this if we didn't have light as a way of measuring it, measuring this distance. And so I haven't even left like the local universe. I've kind of stayed like really close actually till the Milky Way galaxy. And so, we've already passed, it would take longer than the age of the universe for us to try to do this. And so let's just pretend that maybe it's feasible. We could do the most distant galaxy that we've ever measured. So this little red smudge here, this is a galaxy that, this is an image from Hubble, and this galaxy is 13.4 billion light years away, or at least it was when the galaxy emitted its light that we're seeing in this image now. That's 16 trillion beer years. That's 1,000 times. That would take 1,000 times longer than the age of the universe for us to build, this giant stack of cans that we're measuring the universe with. And so, I think the next logical step is, well, what if we tried to measure just the whole universe? That's 13.7 billion light years. We've already seen that, we can't even measure 65 million light years without surpassing the age of the universe. And so, at some point, the universe started expanding faster than we would be able to drink, 7 billion humans drinking 10 weird foot-tall beer cans every single day. The universe started expanding faster than we would be able to drink and stack those cans. And that's all 7 billion of us kind of working together. We just wouldn't be able to catch up to the universe. It would just be impossible. And so I hope you've kind of enjoyed this weird way of measuring stuff. I do have just some key takeaways. The first one is that the universe is enormous. There's lots of astrophysicists that have always said it's so big that the human mind can't really comprehend how big it is. And I really do think that's true. Even the nearest objects to us are just so big that we can't really imagine how big they are, right? 24 Orion's Nebula, 25 light years across. It takes 25 years for light to go from one side of it to the other side. I personally cannot imagine that distance. That's incredible. And so, unfortunately, we can't drink our way across the galaxy, no matter what. I don't know what. No matter what sci-fi you watch or what some weird sci-fi movie or TV show, you just can't. You can't do this. It's impossible. And my last disclaimer is, please don't try measuring stuff in beer cans at home. And definitely don't try to see how long it takes, to measure stuff if you drink 10 beers a day. Just don't do that. That's definitely not safe. And that's my talk.
All right. Thank you, Astroman. And as much as I love beer, I don't think I would like to live in this society you have created where
Well, so I was thinking about that, and after a while you build up a tolerance, and your liver is indestructible. Your liver just works perfectly. It never gets damaged. So I don't think it would be terrible, but nothing would ever get done. Everyone would just be trying to measure stuff all the time.
We're not that far off. As it turns out, I Googled it because I was curious, how much beer does the world consume? And apparently, it's not all in cans, but if it was all in cans, it would be the equivalent of about 300 billion cans of beer.
Per year?
Per year in the world.
Wow.
Just got to pump those numbers up a bit.
Yeah.
More you know.
Only about a factor of 10 or 100 off. That's not bad.
All right, we got a question here from Liz. How'd you come up with the concept of a beer year?
So I cannot take credit for that. My wonderful fiance asked me what my talk was, and I was, telling her how I planned on trying to conceptualize and measure stuff. And she was like, oh, so it's like a beer year, like a light year, but in beer instead. And so full credit to her. She's very clever. Now the concept of the talk is actually kind of recycled from a talk I saw at a different Astronomy on Tap. They stayed much closer to Earth, so it was a little more manageable, but I thought it was just a cool concept and wanted to give it a shot.
So you're saying we're not going to be building a space elevator out of beer cans anytime soon?
I sure hope not.
Man, well, if there are no more questions in the chat, thank you, Astroman. That was a lot of fun. All right. Now, if you have been participating in trivia, or if you like watching for the answers at the end of every presentation, now is your time. All right. Okay. The theme of this month's trivia was astronomy-themed food and drink. What are the following things named for, or share a name with? First up, we have Mars candy bars. Are they named for a planet, galaxy, or an astronomy concept?
Gee, I don't know.
Yeah, I have faith in y'all. You know it was Mars, our lovely, dear red planet friend.
Question number 2, orbit chewing gum. Is it a planet, a galaxy, or an astronomy concept? It's an astronomy concept. You know, orbits being the things that things... I was going to say orbit on, but that's kind of redundant, isn't it? Huh.
Paths that they follow, I guess.
Yes, that's good.
Question 3, starburst candy. Are they named for an asteroid, galaxy, or planet? Just like we have starburst candy, we have things called starburst galaxies. These are galaxies that are really, really actively forming lots of stars over a really short time, like this galaxy that you can see here. All the blue regions are places where the galaxy is forming new stars.
What about Elysian Space Dust IPA? I'm sensing it's a little bias here. Is it a planet, actual space dust, or the sun? It's named for actual space dust. All right, what do you know?
All right, question 5, spaghettification. Is it an astronomy concept, the process of making pasta for astronauts, or the process of making spaghetti for astronauts? It is an astronomy concept, like you learned in Felix's talk. And
I am a fan of somebody making spaghetti for me, so you know, help me out there. What about the Laganita supercluster? Is it a group of comets, a group of aliens, or a group of galaxies? It is a group of galaxies, so you can get superclusters of galaxies, such as in this wonderful image.
You have to believe us. There's a cluster there, we swear.
Yeah.
Question 7, nuclear pasta. Is it the preferred food of quarks, a nuclear physics concept, or the preferred fuel of nuclear power plants? It's a nuclear physics concept that has to do with really weird states of matter. You can end up with structures, let's say, like gnocchi, spaghetti, lasagna, and you've also got anti-spaghetti and anti-gnocchi. I don't know why you would be anti-spaghetti or anti-gnocchi, but there we are.
How does anti-spaghetti affect spaghettification?
Well, the real questions.
Mm-hmm.
You're asking the real questions, Cosmic Kid.
What about the Trappist beer? Is it named for a telescope, planetary system, or both?
It's both!
Wow. Both the telescope and the Trappist one system. That's interesting. Although the spelling's slightly different there.
Yeah. But the acronym for the telescope is TRAPPIST without the E. And it actually fits.
Well, that's new for astronomy acronyms.
I know, right? Anyhow, question 9. Milky Way candy bars. Is it named for a random galaxy, a distant galaxy, or our home galaxy? It is our home galaxy. And if you live somewhere where you can see the night sky like this, you can kind of see it.
If you can take the drive out to nowhere, it's really quite beautiful. And our last trivia question, Space Jam. Shout out to the Space Jam 2 coming out soon. Does this have nothing to do with astronomy? Is it about aliens, or is it just a movie, not a food? Why is it here? All answers are valid.
All right, and that is it for trivia this month.
All right, now let's take one last look at our announcements again. So trivia, we just finished trivia, so hopefully you've completed it. Hopefully you've got 100% on it, and whoever has done the best will be receiving prizes. We'll be emailing you to let you know how we will be figure out how to deliver those prizes.
Right. And you can follow us on social media. On Twitter and Instagram, we are AoT_BCS. And on Facebook, we are AoT BCS. And if you'd like to hear about other Astronomy on Taps happening, you can go to astronomyontap.org/events.
I think I skipped a slide there. Make sure to like and subscribe on YouTube. Hit that bell icon. Smash that like button. Smash that bell icon. It really helps us out with the algorithm and helps us stand out a little more. You know how the AI monster is.
Yep. And please support what would have been our venue in normal times, the Grand Stafford Theater in Bryan. You can Venmo at Jose-Quintana-20 and put Stafford Tip in the description so he knows what it's for.
Help support us on Venmo or the Cash App at AoT BCS. Give us $15 and we'll send you an AoT t-shirt featuring this lovely design that you can see here.
Our next event is Pikachu face. I can't do a Pikachu's face. Never mind. But it will be the third Wednesday. Thanks, Cosmic Kid. Our next event will be the third Wednesday of June, which is June 23rd.
And, well, the live chat's over, but next time, put questions to the live chat. And that's going to be it for tonight's AoT BCS. Thank you all so much for coming. Thank you to our speakers and Dark Matter Dude for
And the Cosmic Kid.
And the Cosmic Kid. All right, I was
Back
saving
after
the
a long
best for
break.
last. Hope you had a great night, and we'll see you next month.
Okay, we're good.